Next, I have the pleasure of introducing our next speaker, Russ Tedrake. Russ Tedrake is a professor at MIT and a vice president of robotics research at the Toyota Research Institute. At MIT, Russ created two courses, namely Under-Actuated Robotics and Robotics Manipulation. Russ also led the development of Drake, a C++ Python toolbox for simulation and optimization-based design analysis of complex dynamical systems. Russ will offer his perspective on the topic, many views of robustness, from robust control to foundation models. Please join me in welcoming him on stage.
Thank you very much to the organizers. It's been fun. I guess maybe I surprised some of you in the panel conversation this morning. So maybe I'll tell you the story that got me there, and then I'll try to connect it back to the robustness theme at the end here. So we started TRI in 2016. We started a team called the Dexterous Manipulation Team. And it's interesting to think about what you can do in industry versus what you can do in academia. But one of the things that I feel is different in industry is we can do larger scale projects than I would be able to do at MIT. Some of you have big projects in academia too, and we go after challenge tasks. Okay, so we decided years ago to start with our first challenge task, which was loading the dishwasher. Okay, as a C1, he would dump random stuff into the dishwasher, and we would have our robot basically go all day long trying to take the mugs, put them in the top shelf, the plates, put them in the bottom shelf, the silverware, put them in the top silverware rack. Anything that didn't fit any of those above would be thrown to the side. Okay, and if you think about the time that this happened, 2016 was right when deep learning really started coming into the field, and we could do object recognition in ways that we couldn't before, right? So we asked a lot of questions about how we could do something complicated like this, like the more dexterous skills of picking up a plate. This was a favorite for me. Actually, it was a pretty subtle skill that we had to get right. C1 did a lot of work on that particular skill. It was mostly a hand-coded sort of state machine kind of controller. And you can see sim and real next to each other. And we did a lot of investment in simulation. But we were also trying to answer fundamental questions about robustness of a system that had machine learning in the loop, right? So we asked robustness at the task level. We couldn't kick our quadrupeds, so we just shut the dishwasher drawer. Not quite as cool, but that's what we could do, yeah. And we started doing massive scale. We really invested a lot in simulation. So we did really large scale testing, Monte Carlo suites running in the cloud. Every morning we'd wake up, we'd see what broke. If we put a git commit in, performance got worse, we knew about it in the morning, and we would play this battle. And we would try to we got our system to a pretty darn high level of reliability, right? And it was very fun to go through this exercise. We found some very subtle bugs just from large scale simulation-based testing in the cloud. One of them, I won't tell you the whole story here, but basically there was this weird interaction between the perception system, the noise model, and the task level planner that was like a whole end-to-end kind of thing that you would just never have caught with a unit test, and you really had to catch with large scale end-to-end testing. Okay, and it was because we were making the simulation, Monte Carlo suite much harder than reality. It was, it was like you're always driving through downtown New Delhi, or your dishwasher's always going like this, right? But it turned out the system, the bugs we found in simulation that way did eventually manifest themselves in reality, and we were able to do very well with that. Okay, so the point we got to when we were winding down the dish loading project was we said we've invested a lot in simulation. We've invested a lot. I've invested a lot of my career in model-based control. Okay, and so we wanted to ask sort of what's the existential threat to that view of the world, right? And the existential threat was that you can't model everything yet in simulation. Okay, so we wanted to pick our next challenge to be a challenge that said, how do you do good control when you don't have useful models, right? So many things we could have picked. Laundry folding is a good one, various tidying up around the home is a good one, but we wanted to lean into food preparation because there's just so much diversity that you can bring to the robot for $5 for a sack of potatoes at the grocery store, and you get all kinds of diversity that's hard to get in simulation. You get deformable, you get liquids, you get all these things very easily. And it's interesting, so we go through our playbook, and all that simulation work we did by choice was not immediately relevant. Now, interestingly, of course, the simulation team is chasing us and simulating more and more of those tasks incredibly well. Okay, doing reinforcement learning in simulation and then transferring it was not immediately in the playbook. Okay, and anything that involved state estimation, by design, sort of was not in the playbook. So at the time, we tried a couple different sort of angles. Let's see if we could learn a dynamics model. You might call it a world model. I refuse to. It's a plant, okay? Or we could try behavior cloning. We were seeing the beginnings of people really having success with behavior cloning in the form of imitation learning. And it started working so well for us that we leaned pretty hard into behavior cloning. Okay, and it started for me actually at MIT. I think I saw Lucas earlier, Pete and Lucas and Yunzu's also here. They were doing experiments with visual motor policies using behavior cloning at MIT. This is back when we were doing dense descriptors. Okay, and this, I think, really changed my worldview. I think for a couple of reasons I'll outline, but these systems worked incredibly well on the real robots. You could come in any day, you could see the demo, as long as nobody bumped the camera, but the robustness to visual distractors, which I was very worried about once we were closing the feedback loop through RGB, it just worked very well, to the point where it really made me sort of, question things, right? So there's, deformable things were happening, weird distractors, and there was just a sense of robustness that I hadn't seen before when you had a state estimator in the loop. Okay, so I was forced to reflect on my core beliefs, okay? And here's the first takeaway is I will never ignore RGB again. Closing our feedback loop through RGB at high rates is so valuable that I cannot ever ignore that again, okay? I don't actually love imitation learning, right? I think decision-making is more than mimicry, okay? But it's a super clever way to explore the space of policy representations. So I was sort of like, okay, let's play with imitation learning for a while, and then we'll figure out how to do it, for real, okay? But it's going really far. So we're still doing imitation learning a lot, okay? And the reason it's so clever is because when you know this, right? But you don't need a model, right? You don't even need a state representation, and not just for the plant, but also even just to specify the objective, right? That's a big deal. Like I'm just mimicking the demonstration. That's way easier than trying to find some instrumented way to make an RL sort of objective. Okay, so we've been exploring this space of policy representations and found something good in this diffusion models, right? So this was a fantastic project with Sharon. I don't know if Sharon's around. And Chung came and spent the summer as an intern at TRI, and we tried this new version. We were already doing a lot of behavior cloning, but Chung's project was to try the diffusion version of this, and it's just worked incredibly well. It's changed our pipeline. So now we have, if you were to come to TRI today, you'll see robots doing this kind of stuff. So I know in my classes, I've said for a while, like, there's some problems that are really hard. I don't know how to make a robot spread peanut butter on toast, right? I buttoned my shirt. I had a few of them, okay? This is chocolate hummus, which I didn't actually know was a thing, but it was a little better than peanut butter to have around the lab. And then, turning a piece of paper, peeling a potato. They've done almost all of the ones on my bucket list. And then I said, there's one thing, you have to tie shoelaces. And well, both, I don't know if our hands are dexterous enough yet, but also Toffee, our manager, joked. She said, "Don't do that because we don't want Russ to retire just yet." Because I was kind of like, maybe I'm done, Anyways, but it's pretty amazing. So these are potentially bimanual tasks. They're still visually robust in the way that that we saw originally at MIT. The thing that impressed me. Okay, these are tasks. Actually, this one was really interesting because it's not only bimanual, but it's highly kinematically constrained, right? There's a kinematic constraint in the crank, and we can do it with eggs too. This particular video didn't have the eggs, okay? But very compelling for me. One day, Naveen sort of picked, so every day we're just kind of trying to invent new things to try to train the robot to do. And one day Naveen says, I'm gonna do dish loading. The thing we spent like 3 years programming before, let's try doing that. And in like 3 hours, he came up with a dish loading demo, which Siwan graciously came back and said, even though he was the one that spent the 3 years on it, he sort of graciously came back and said, that's just as robust, or if not more robust than what we did back then, right? So that's, it's a big improvement, right? This is just, like any day you can sort of go on Slack and see what are the best new rollouts, right? And The only reason this is from Thursday is because TRI has Fridays off. Okay, but you know, they were rolling out mats. Okay, just people are coming up with random new skills. You could come to TRI and you could have a random skill, and if you're willing to demonstrate it 50 to 100 times, you know, then and wait for the GPUs to train maybe, and then come back, then we would be able to show pretty good rollouts. It's really very compelling to me. And we're going to have a demo on Wednesday where you'll be able to see. We're going to be running the robot live at TRI, and you can ask all the experts the details. Okay, so the architecture of diffusion policy is somewhat standard, and you know, it's what you would do if you were to put all these tools together, right? So ResNet backbones. A few people asked me about how many parameters in the single skill task. We tend to have between 110 and 150 million parameters. We're still using UNets in the denoiser for diffusion before, and importantly it's taking a history of observations and predicting a forecast of future actions. Okay, so a lot of people ask why diffusion, and I don't think it's an exclusive choice. Okay, but there are some reasons that we like diffusion. I mean, first of all, it just seems to be able to absorb the data that we're putting in, even when we're getting to the multitask version of this. It seems to have incredible capacity and great performance. Okay, the fact that we're doing as well as we're doing with a small number of demonstrations is surprising to me. We're still trying to understand exactly where that comes from. One of the key things was the ability to deal with multimodal demonstrations, right? So a lot of work was going into trying to do energy-based behavior cloning. Categorical distributions work great, no question, but this was the way that started working really well for us for continuous distributions. More subtle things, right? But those of you, I mean, all of you know this, right? But the fact that we have training stability and consistency and no more hyperparameter tuning, right? We don't touch those hyperparameters. We run the same number of training steps. We know exactly where to come back every day, and there's no more hacking around with that. That's a huge difference maker to make this really go into a larger scale. It generates high dimensional continuous outputs, right? So originally, of course, born with images in mind, and I think people don't seem worried about RT1 and RT2 using categorical. I think it can work. I feel like it should be continuous at the bottom. ACT is continuous at the bottom. I think there's many ways you could do it. The capacity and these other features are important. Okay, but one of the things I like, and maybe this is me just being old, is I do like that the diffusion model has very solid mathematical foundations in score functions and learning the log of the probability distribution. And in particular, whereas transformers, I mean, so you can use transformers with diffusion, of course. You can use your denoiser as a transformer. Those are not exclusive. But I like that these models sort of asymptote nicely in the case of a simple, if you take a simple linear system and you demonstrate from the optimal linear control, then you'll get back something that looks like LQG unrolled. And that gives me the ability to think a little bit more clearly about these things and maybe make contributions that go back up to the big complicated case. Okay, so the way I want you to think about this, the way I think about this is that this is a control policy. It's still absolutely an output feedback control policy, right? It's taking a history of inputs. It's producing a history or a future set of outputs. Okay, the diffusion policy is an autoregressive model with forecasting. So it's taking the history of observations, but it's producing actually a forecast of future actions, which is essential actually, in ways that I had to get my head around, and we're still maybe seeing it all the way through. Of course, the conditional denoiser produces the forecast conditional on the history. So, I say it's good at doing multimodal demonstrations, handling multimodal demonstrations, but we also know that behavior cloning sort of fundamentally wants stability, right? Because you don't want to walk away from your training data and get out of domain. So it's actually interesting. You have to think that those are in tension. You would think that those are in tension, right? How can I be in the same state, possibly take different actions, but be stable? Okay, those things feel like they should be in tension. But because it sort of boils down to like, a simple model and we're seeing it through the lens of these forecasting models, you can understand that it is possible in these models to have, funnels, if you like, that still go left or right around the obstacle. That's a very simple picture, but I think there's clarity that can be obtained by thinking these ways. Okay, I don't want to say that it's only diffusion, it's only large models. I think there's these results were built on a big stack of enabling technologies, right? So one of them was a haptic teleop interface. So you see the haptic device here. This task in particular, when you don't have haptic feedback, so the human cannot feel the forces that the robot feels, then it's very hard to execute that constrained manipulation. You'll kind of naturally jam. You certainly can't go as fast, okay? But once you can feel what the robot feels, at least Eric can go super fast. I can't go as fast as Eric can. Okay, so that's just an important essential tool, okay? It's built on excellent engineering, right? There's really good system ID, really good robot control. So this is an example of the human basically trying to make the robot collide with the table, and the robot is refusing because it's just got a low-level operation space control with collision avoidance. Even when you try to jam the robots together and there's complicated collision geometries, right? Those are things we do know how to do in robots, and you can put that as a nice last layer of protection. Maybe it's our safety case, if you like, for making these things have robust rollouts. Okay, and some of this, you'll notice that some of those demonstrations use visuotactile sensing. So that funny large bubble thing that you see, that's the TRI soft bubble gripper. Okay, there's a camera inside that. The deformations of the bubble correspond to the forces that the gripper's feeling, and even the stresses and strains that the gripper's feeling because of the patterning on the inside of the bubble. Okay, and some of those tasks were fundamentally more robust because of the visuotactile sensing. Maybe not surprisingly, but we wanted to be careful about evaluating that and seeing that. Okay, so we've seen something good in these diffusion policies, and so naturally we're trying to scale this up, right? So we're training lots and lots of skills now, including last Thursday, and scaling fast. Everything I said so far was about training one skill, okay? But of course, what everybody wants is few-shot generalization to new skills, which means multitask, language-conditioned policies, right? And finding ways to connect that to the internet scale data so that we don't have to make ImageNet size or bigger size data for, just on our robots, okay? Of course, there's big questions, which we only have, beginnings of answers to, about how do we actually feed that data flywheel. We've been talking about that throughout the day. What are the scaling laws? How many skills are we going to have to pump into this thing before we get zero-shot generalization out? I can't tell you the answer to that yet, but we're sure thinking about it. I don't see an immediate ceiling. So it put me somehow on the debate this afternoon. I got on Sergey's team today instead of on Scott's team because I said something like that. Okay, so I do think there's something deep happening here, if you will, right? I think manipulation as a control problem is relatively easy, right? So it's not at the limits of control authority. It's not, there's no stability issues really to think about. This should be an easy problem. It's probably low dimensional. The images are probably low dimensional, and a lot of the complexity comes from the images input to the manipulation system, right? And in those domains, I think memorization really can go a long way. Well, far enough to be extremely useful, okay? I do still believe in work in model-based control. Just to, if you didn't hear me say that this morning, I still, I believe there are some fundamental truths, and model-based shows me how to see them in some ways, and this is helping me see them in different ways. So the main question of the workshop is, how should we think about deployability, right? So let's just take a minute to remember a few of the lessons from control. And it's maybe to say some things a little different than what came out this morning. But so my background in control, right, I've done things like airplanes landing on a perch, okay? But when we did those with kind of a robust control type toolbox. So we had a model of the aircraft, we had a model of the uncertainty in our model, and we had a model of any possible disturbances, and we computed reachable sets, right? And we used very powerful toolbox from Lyapunov and robust control theory, okay? You can extend that to some extent to small neural networks, right? And we've done that. Lots of people have done that better. We were able to sort of do closed loop analysis of systems that have neural networks in the loop with Honkai. And so let's just think about some of the lessons there. And does that apply? And is that going to scale, right? So that standard approach would be to say, I've got some nominal model, right? And some uncertainty model. So I have state, I have inputs, and then I have some disturbances coming into my arbitrary nonlinear function potentially. But I'm going to say that those disturbances come from some uncertainty set, right? Domain randomization is just this. It fits right into this, right? So you're going to pick some lighting conditions. You're going to pick some texture maps to apply. You're going to pick some terrains to walk over. That's just, the new way to say W. Maybe before I would have said it's a polytope or something, and now you're saying it's a texture map, a library of texture maps, but it's really the same kind of idea, okay? Robust control sort of infamously optimized worst case performance. But I think people think, oh, that's because, robust control people are like uber conservative. And I just want to push back on that a little bit, because that's not what happened, right? I think robust control people are very smart, extremely smart, okay? But the idea is that if you have to put a distribution over W in order to do something like an expected value, optimize the expected value, then that's a stronger assumption about what you're saying about W, right? If you just say blanket, it could be anything in this set, then that's actually a weaker model of the uncertainty, and we shouldn't expect to know the uncertainty. Okay, so let's just remember that I think the goal in robust control was not to be uber conservative. It was to say I don't claim to know the world. Okay. When you try to take that to the open world setting, and you ask about verification, those models are, very hard to think about. And I would say I don't believe right now that the Lyapunov worst case analysis is the right way to think about autonomous driving or open world manipulation, right? So we instead took a much more statistical, and this is our version of what all the autonomous driving companies are doing, for instance. We looked a lot more into statistical statements about robustness, rare event simulation, these kind of tools. And those, again, are finding surprisingly rare and diverse failures, of complicated systems. Okay, but it's still, just to make sure I say this clearly, right? So, just say one more thing before I say it clearly. Yeah, the key idea there was that we had to not try to find single counterexamples that made the system fail, but actually try to estimate the probability of failure, because you want to have diverse counterexamples, okay? And it's really a hard game to play, right? Because then you want to build these uncertainty sets that should excite all of the ways that the system can fail. But if you make that distribution too big, then you get all kinds of false positives, and you're wasting your time saying like, oh, that was a bad rollout. That would never happen in the world. Okay, so this balance is very, very tough. Okay, but the essential point is, like, in both of those cases, in the robust control case or in the stochastic, Monte Carlo stress testing case, we're explicitly not trying to certify the performance in the real world. Okay, it's different. It's that we're going to pick an uncertainty distribution W, right? Which if I'm trying to be robust to this, then that should make me robust to things in the world, even the unknown unknowns. That's the philosophy that I subscribe to, is that synthesizing against a robust objective is good. But I typically stop short of saying, I've certified that it's going to work in the real world. That's a long tail to deal with and a very hard statement to make. And I don't know that it's necessary to be successful. And really, the foundation model quest that we're all on is taking this just to the next level in some sense, right? Where the mentality is, now let's just grow the data set on real data until everything is in distribution, okay? So it's a different way to specify W, but it's still somehow a way to specify W. But the essential point, and this came up in the panel this morning, is that the type of robustness that is possibly coming out of that, which was not visible in the more narrow specifications of the task, is a sense of sort of common sense robustness that we just, I think, cannot underestimate the potential for that, right? That if you can do many tasks well, then you'll have a potential ability to respond to very out of domain things for a narrow task. And the philosophy also changes where failure is as good as long as, I mean, I'm not going to ask it to drive my daughter to daycare or anything, but safety critical is a different question. But I think non-catastrophic failures are good as long as we show recovery in the demonstrations, for instance. And I think as we go to deploy these systems, we'll have business cases, and like Scott talked about, having extremely good tools to scrub our data, get data back, and be able to replay and capture and repair fixes after the system's deployed. We must, right? Okay, so how do we get to deployable, right? I think we have not yet seen what robustness looks like when we get our sort of GPT moment for robots. But I'm optimistic. I think that's. Don't ask me to predict how many months, but it's something we must be trying for, right? And I would bet when we get there, even if we don't have a safety case, that we'll be happy. It'll be valuable enough that it will be deployable. So that's my answer to the workshop question. Yeah. Okay, that's it. Yeah.
Thank you, Russ, for the insightful discussion. Any questions from the audience? We'll take 2 questions.
So in the beginning, you showed some videos of like loading and unloading dishwasher, and then at the end, you showed like some more tasks with diffusion policies. One thing that I noticed is like task complexity versus scene complexity. And like with diffusion, you showed like a lot more capabilities in complexity of the tasks, but the scenes or like distractor objects, the level of clutter seem to be much more organized and cleaner way, like in diffusion, like the later examples. How can we address that so that we are not only multitask, but also robust to like real world clutter, and maybe like some of the low data regime is byproduct of not having distractor objects, maybe like,
It's a great question. So I mean, there's a couple layers to that question. So it's true that we, especially at the beginning, we were behavior cloning things that were much more narrow, like shorter horizon tasks. We were not trying to load the entire dishwasher. In fact, that dish loading example was actually, Naveen tried that, and we were all like, that's way too long horizon to be successful. And it just kind of powered through and was more beyond our expectations. It worked. Okay, so we have not yet, I shouldn't say we won't, but we have not yet tried to do that 60 demonstrations for like entire long-term tasks. Not to say we couldn't try, but I think that's maybe not the shortest path. What we're instead focusing on is this multi-skill framework, conditioning on language, okay? And then some of the power of reasoning of large language models and other things come into play for the task level reasoning. And of course, large language models should be able to use tools and stuff like this. So it's not clear to me that the low-level skills, even if they have to be, so there's of course proposals to try to combine those into skill libraries and then compose them explicitly with a planner. It's a good idea. But even if we don't do that, I think there's reason to be optimistic that it can accomplish multi-step, long horizon tasks by assembling the learning-based tools we've already seen. Yeah?
I guess,
Okay, sure.
Yeah, thanks for a really nice talk. So I have a question about behavior cloning and vision. So, when you have tasks that are heavy on vision and, where the trajectories critically depend on vision, then how can you sort of make, your demonstrations similar to what the robot sees, through its perception pipeline?
Yep.
Because I think behavior cloning is dependent a lot on the trajectories that the human is providing.
Yes.
Right? So if you could just comment on integrating vision into behavior cloning.
Yeah, so that's a really good question. So, of course, it's deeply connected already in the sense that we're using cameras to close visual motor policies, okay, and visual tactile motor policies, right? But no, your point is good. So that if it's, I would say maybe rather than using cameras, it's more about partial observability and making sure that the human demonstrator demonstrates the necessary information gathering actions or whatever in order to accomplish a partially observable task. And I think you're right. If we give the demonstrator omniscient information and the controller is more impoverished, then it's not going to succeed. But I think there's, you can go into a more immersive, so you see the robot sensors, take the Avatar X Prize sort of demonstrations, and I think limit the human in ways that the robot is limited. Again, as you add partial observability, you're extending the horizon of some of these tasks, and the reasoning is different. I would say I'm optimistic. I wouldn't say we've studied that as much yet. It's a good point.
Great discussion. Let's thank Russ again.
Sure.